Okay guys, this is the empirical formula video. First term you need to be familiar with is percent composition. And anytime you do the percent of anything, it's always going to be part divided by whole. So what we have is the whole or total mass of the compound. And we're going to divide the mass of each element by that compound. So however many elements you have, that's how many percent you should have. So here's our problem. Find the percent composition of Na2CO3 dot 10H2O. All that means is that's a hydrate, and what it means is on each salt molecule there are 10 water molecules attached to it. So we got to add up all the hydrogens and all the oxygens in the whole thing. All right, so when you do that, when you have the mass of 2 sodiums, a carbon, 3 oxygens plus 10 oxygens, right? You got to distribute the 10, and you got to distribute to the hydrogen. So we have a total of 13 oxygens. From there, we have a total of 20 hydrogen. We have 1 carbon and 2 sodiums. Okay, when you total that up, the mass that you get for that is 286 grams per mole. So here's what we're going to do. We're going to take the mass of these 2 sodium atoms. Look on your periodic table, they're each 23. So that would be 46. 46 divided by our total molar mass gives us the percent mass of sodium. Next, we'll have 1 carbon, and that's 12 grams per mole, divided by, again, the total, gives us 4.1%. And we mentioned we have 13 oxygens. So 13 times 16, which is its molar mass, gives us 208. See, the most of the molecule is oxygen. And then finally we have our 10 times 2, 20 hydrogens. So 20 divided by 286 gives us our 7.1%. Okay, so that's how you do percent by mass. Next we have empirical formula. And it's the smallest whole number mole ratio of the atoms. So for example, if we have C2H6, that's not in reduced form. We could reduce it to CH3. C3H12, that's not in reduced form either. We can reduce it to CH4. Okay, so divide 3 by itself, divide by 3 by 12, and it gives us 4. Okay, so next we have molar mass. We already know that. That's just for review. Okay, get that from your periodic table. Next, formula mass. Now notice the difference between formula mass and molar mass. Molar mass is grams per mole, and formula mass is an AMU. So formula mass is going to be for 1 formula unit or 1 molecule. 1 single little itty bitty teeny tiny molecule. The empirical formula mass, that's the formula mass in lowest terms. Okay, and then the molecular formula mass, that's the actual formula of the compound. Okay, so it's not necessarily in reduced form, and here's why. It's not that we care about the empirical formula mass, it's just that's one of the steps in order to get our final answer of the molecular formula, the actual real formula of the compound. Okay, simple 3 steps to finding the empirical formula. First step, go ahead and convert the mass of each element to moles, so convert grams to moles. You guys know how to do all that. And then divide each of the moles by the one with the least number of moles. And then finally round each to the nearest whole number if it's close. If not, multiply it by the least common factor. Okay, so let me show you what that looks like. Okay, here's our sample problem. We have a percent composition, and remember, percent composition is percent by mass. So 54.5% carbon, 9% hydrogen, 36.4% oxygen. So first step is to convert grams to moles. You may be looking at that saying, wait, we have percent, we need grams. Well, it's percent by mass. So simply all you have to do is just drop the percent and add grams to it. If that doesn't sit well with you, look at it this way. We can have any quantity we want. So let's say we have 100 grams of our compound. If we have 100 grams of our compound, 54.5 grams are carbon, 9.1 are hydrogen, and 36.4 are oxygen. All right, so first step, convert grams to moles. So what we did, let's ignore this for a minute. Okay, so let's ignore this for a minute. I don't want to mess you up. Okay, so first step, convert grams to moles. 54.5 grams of carbon, divide by its molar mass of carbon, which is 12. That gives us about 4.5 moles. 9 grams of hydrogen. Okay, the molar mass of hydrogen is just 1 gram per mole. It gives us 9.1 grams. 36.4 grams of oxygen divided by its molar mass, which is 16. And here's how many moles of each we have. So the second step is divide each of these by the least number of moles, which happens to be this, 2.28 moles. So we're going to divide each of those by that number of moles. Okay, so we divide each by the least number of moles. When we divide 4.54 moles divided by 2.28 moles, that gives us 2 moles of carbon. We divide 9.1 divided by 2.8, that gives us 4 moles of carbon. And oxygen just divided by itself just gives us 1. So that's how we get the empirical formula. Now we need the mass of the empirical formula. So what we're going to do is we have 2 carbons. So we need to add the mass of 2 carbons, which each are 12, so that's 24. 4 hydrogens, the mass of those. And then finally 1 oxygen is 16. That gives us a total mass of 44.0 AMU. Okay. Now if you notice in the problem, it gives you the molecular formula mass is 88.0 AMU. So we got, for this formula, empirical formula, we got 44 AMU. Well, what we need to do, find out, is what's our real formula? How, in other words, how many times larger is our real formula than our empirical formula? Because remember, empirical formula is just a step that you have to go through to get your final answer, the empirical formula mass. So what we do is we divide our real formula mass by our empirical formula mass and gives us 2. So what that means is our molecular formula is twice as big as that. So let's multiply everything by 2. So that's going to give us C4H8O2. Okay, so that right there, that right there is our actual formula mass. Okay, so that will conclude our notes. So just the first slides for tomorrow. So tomorrow when you guys come in, we're going to practice these types of problems. Bring your notes with you. See you tomorrow.